All right, so now we're going to revisit exponential functions, which are very appropriately named. What word do you see in exponential? You see the word exponent. And the reason that exponent pops up is because exponential functions are defined as functions where the variable is in the exponent. So if you see a variable in the exponent, you have an exponential function. For example, a to the x, where a is just a constant and x is our independent variable. We define this as an exponential function with base a. Now, just a quick review of your exponent rules. You might want to pause and just look over these. You should be familiar with them by now. Now, let's take a look at half-lives. This is one of the most common applications of exponential word problems. A half-life is the amount of time it takes for half of a substance to change from its original radioactive state to a non-radioactive state by emitting energy in the form of radiation. So, for example, let's say we have a half-life of 3 days, there's 24 grams of whatever this substance is, and we want to know how much do we have after 12 days. Well, the first way we can do it is just work it out by hand. Say 3 days go by, you had 24, now it's cut in half. Now we have 12. And then you just do it again and again and again. After another 3 days, let's see, we're up to 6 days total, we also have 6 grams left. After another 3 days, we're down to 3 grams. After 9 days, another 3 days pass, and we have 1.5 grams. That's after our 12 days. But obviously, we want a formula so that we can actually solve this in one step without actually writing it out. But the writing it out can be a really nice check for these. So we have our initial value of 24 grams. It's getting cut in half every time. And that's going to be our base for this exponential function. This is an example of exponential decay, which we'll take a look at in a second. And we're going to raise it to the length of time we're interested in, divided by the length of the half-life. So it's raised to the 4th power, essentially. And if you work all that out, you're going to get the 1.5 grams that we had in the first instance. So half-lives are really common. Just make sure you familiarize yourself with them. Now we're going to take a look at what makes an exponential function a growth function or a decay function. So we're just going to define these functions in general as having some constant out front times a to the x, where a is our base. A growth function has an a value that's greater than 0. A decay function has an a value that is between 0 and 1. And again, the a value here is the base of the exponential function. So the most common growth function looks like this. I think we're all used to seeing a growth function look like that. But what's important about growth is that it could also be flipped upside down if that constant out front is a negative. So this is also technically a growth function, even though we traditionally see it as quote-unquote going down. It is a growth function. And the reason that you can think about this as a growth function is look at the first one. Let's look at some increments on the first one. Can you guys see how the slope is increasing on that first one for that growth function? Well, the way that we think about something as being growth is not that the slope is increasing, but the fact that the amount of y change is getting more and more dramatic every step of the way, right? The change in y is getting more extreme. And that's also what's happening on the flipped growth function. You can see the y values are getting more extreme as you move to the right. So for a decay function, kind of the same idea. Again, you guys are familiar with what a traditional decay function is going to look like. Starts high and then kind of flattens out at one of those asymptotes. We'll draw on those asymptotes in a second. But you can also have the flipped decay function if, again, the constant out front is negative. So just be familiar with that. And we do the same thing with the increments just to show what decay really is. The change in y is really dramatic at first, but then it kind of levels out as you go, as you approach that asymptote. Same thing on the flipped function. At first, it looks like those changes in y are really dramatic, but then they kind of flatten out. And again, yeah, let's just draw those asymptotes in. The asymptote is a line. It's a horizontal line in these cases that your function is going to approach, but never reach. So as your function approaches the asymptote, the distance between the asymptote and the curve gets smaller. Another application is compound interest. We've got the compound interest formula right there that you guys should recognize from pre-calculus and Algebra 2. I'm not going to go through defining everything in that formula. You should be familiar with it. Let's just say for an example here, we're depositing $2,500 in the bank with a 5.4% interest rate, and we want to know how much money am I going to have after 10 years. These problems are always assuming that you're not actually depositing anything beyond the $2,500. You're just leaving it in the bank and not touching it. So The key here is n in that formula. N is the number of compoundings per year, which is the thing that I think students struggle with the most. So the number of compoundings just refers to the amount of times that you apply the interest. So annually, your n would be 1, quarterly, your n would be 4, monthly means every month you're applying 1/12 of that interest rate, and you can see the values that correspond. Continuously compounded interest uses the PERT formula, which again you guys should recognize. The E in the PERT formula is the number E. And continuously compounded interest is this idea that you are just continuously applying some fraction of the interest rate. So let's look at a couple more examples. Let's say that I want to compound my interest daily. That increases the number of compoundings to 365. That means that we should have more money, than the monthly case, because you guys can see that the amount of money was going up as the number of compoundings was increasing, and sure enough, it's about $5 more. But what about continuously? So this is where we use our PERT formula. You're no longer plugging into the original. And it did go up, but notice how the change is very, very, very small between daily and continuously. And if you think about it, that should make some sense. I mean, daily means that you're applying 1/365th of the interest, every day for a year. Whereas continuously is kind of this abstract idea that you are just always applying a sliver of that percentage continuously throughout the year. But that difference is just so small that it doesn't really amount to that much money in the long run. There is though a dramatic difference between the number of compoundings being annual, right, where you only have n is equal to 1, and having that daily interest rate. So hopefully that helped review some of the essential applications and kind of a general overview of exponential functions. Again, I highly recommend that you guys take a look back at the properties for exponent rules if you haven't seen them in a while. Make sure you familiarize yourself with them.